All right, so in the previous segment, we looked at what it means to have a change in observer, which is a change in basis or change in reference frame. And we also saw that when we talk of a change in basis with respect, and when we're looking at the body in its current configuration, right, this sort of a thing, it is completely equivalent to keeping the basis the same, but just having the body translate in the opposite direction and also rotate the other way. Okay? We're now going to look at what needs to happen with constitutive relations in this context, right? Essentially, we want to understand what it means to have invariance with respect to rigid motions on the current configuration, what it means to have constitutive relations that are properly invariant. Okay? So, we're going to do this by first looking at an example. Okay? So, we're now going to look at the invariance of constitutive relations under rigid motions. Okay? Okay? Importantly, when we talk about rigid motions on omega t, we're really talking of these kinds of situations, right? We already have a current configuration. We already have a deformed configuration. We're talking of further superposed rigid motions on this configuration. Okay? And the reason, again, to flog a dead horse, the reason to do this is that it is completely equivalent to doing that, right? Changing basis. Okay. So, let's just remember what what needs to happen with the various classes of objects that we have here. Okay, so we have now the notion of objective scalars. Okay, a scalar is said to be objective if it does not transform. A scalar that is objective with respect to WRT, acronym for with respect to. So a scalar that is objective with respect to rigid motions of omega t satisfies rho plus x plus comma t equals rho x comma t, right? Right, where x plus is c t plus q t x. Okay, C belonging to R3, C being a vector, and Q belonging to SO3 plus. Okay, so that's what happens with scalars. This is what we mean by objective scalars. Objective vectors now I'm going to dispense with the statement. Okay, I'm just going to give you the transformation. Okay, and remember we're talking about the scalar components. Okay, a vector is invariant. The vector remains the same, right? It's just a matter of its components. So objective vectors. Okay, so maybe I should say that objective vectors, the components transform as u plus equals q u. All right, and objective tensors okay, the components transform as sigma plus equals q, the matrix of components without the rigid motion, q transpose. Okay? All right. With this as background, let's consider an example now. Let's consider the example of the ideal fluid. Okay, and in particular, let's look at the ideal compressible fluid. Okay, okay, and that constitutive relation for the Cauchy stress was sigma equals some function of the mass density multiplying the isotropic tensor. Okay? Right, we've studied this. Okay, so what happens now is that we have a change in basis, right? So what we're looking at is this sort of situation. We have an example here, right? So okay, so let's suppose that we have a beaker, right, with a fluid in it. Okay, that's a fluid. Okay, and what we're trying to do here is the following, right? We have that as our basis. Okay, and this is the current configuration of the fluid, right? This is omega t. Okay, right? So now we're applying a rigid motion on that current configuration, right? So we're sending that current configuration off to okay. Okay, let's say that's omega t plus. Okay, and then if there's a point x here, we know that we get to a point x plus, okay, where we have x plus equals c t, and clearly we can see the translation. We can see as well the rotation here. Okay, so under the situation, of course, so in general, the stress components after the translation and rotation are going to look different, right? And what we are told is that we need to have sigma plus is q sigma q transpose, right? This is what we know about the stress tensor, right? Because it is a tensor. On the other hand, we already have a constitutive expression for sigma plus, right? Which is what this is, right? So we could just evaluate that constitutive relation. Now, P is a scalar, depends upon a scalar, which under the transformation becomes rho plus, okay, times the isotropic tensor in the new configuration. But the isotropic tensor, after all, is a constant, right? So we have that isotropic tensor stays the same. Now, P is a function of rho, right? And in the new configuration, it has to be evaluated at rho plus. But we know that scalars remain the same, right? So rho plus becomes rho. Okay, so what we should see is that sigma plus is the same as sigma. Okay, but then we do indeed have that. Okay, right? Because if we go back here and evaluate this, we basically get q acting on P rho isotropic tensor Q transpose, right? Which, because of the properties of the isotropic tensor, is just P rho. Okay? So what we see is that the expression for the constitutive relation that we have and that I've circled at the top of the slide is an objective function, right? It satisfies, specifying that function satisfies the basic rules of transformation of tensor components under rigid body motions. Okay? So what we're saying is that sigma equals P rho is objective, right? It is objective as a constitutive relation. The constitutive relation we have in this case was one for the tensor, and it does indeed obey the rules of tensor transformation under rigid motions. Okay, so I'm going to go to the next slide and write that out. The tensor constitutive relation obeys the rules of tensor transformations under rigid motions. Okay, and this is what we mean for this tensor constitutive relation to be properly invariant. This is what we mean by its invariance. Okay, this is the proper notion of invariance. Okay, for the tensor, or maybe I should call it tensorial constitutive relation. Okay? All right, so that was an example of how things ought to work, and this is what we mean by invariance of constitutive relations under rigid motions. Okay, what we're going to do from here is to go on and look at the case of hyperelastic solids as well as the case of non-ideal fluids. Okay, in order to do that, we need to just look at how some of the relevant kinematic tensors or the kinematic quantities, what happens with them under rigid motions. Okay, so let's look at this. Okay, so what we need, let's suppose then that we have this sort of situation, right? We have the basis. Let's suppose that this was the current this was the reference configuration. Okay. The body undergoes a deformation into the current configuration, and I'm going to try and take some care here to draw a current configuration that I can properly, that I can draw a reasonable rotation of. Okay, so this is phi. Okay, this is omega t, and that point is gone to little x. Okay, that's the deformation. Now we're applying a superposed rigid motion on the current configuration. Okay, so that current configuration goes to it has deformed in my drawing, but it's meant not to have deformed. Okay, so What we have now here is omega t plus, okay? And if we write the total motion of this configuration, that point has gone to x plus, okay? And we're saying that the motion between omega t and omega t plus is meant to be rigid. But what that says is that we can compose the total motion, right, as phi plus, okay, equals c t, right? That's the translation from omega t to omega t plus, plus q t little x. Okay, that gives us the total final configuration. Okay, all right. So this is the situation that we have, and what we're going to do is look at the deformation gradient. Okay, we know that f equals partial of phi with respect to x. Okay, but that gives us the mapping of the tangent map for that part of the motion. Okay, what about the rest of it, right? So essentially, what is the tangent map for, well, I'm going to have to break up this tangent map. What about that tangent map? Okay, I should say that f is this guy. All right, what about that tangent map? Okay, that's easy enough. We know that f plus, just follow the definition. F plus is derivative of phi plus with respect to x, okay? And observing what phi plus is, we know that there's a derivative with respect to x of c, function of time, plus q, function of time, little x, but little x, remember, is just phi. Okay? So when we calculate these derivatives, we see that the first term, c, gives us nothing because it's a function of time alone. Q also is a function of time, right? Phi, however, which is the same as little x, phi does depend upon position, does depend upon the reference position. So when we carry this out, what we see is that for f plus, we get q, function of time, partial of phi with respect to capital X, but then we know that partial of phi with respect to capital X was the original deformation gradient. So we have here q, function of time, f. All right? This is how the deformation gradient transforms. Okay? Right? So we have f plus for rigid motions is qf. Observe that it is not qf transpose, which is the way objective tensors transform. Okay? So we have the situation where this is the proper transformation for the deformation gradient, but what this also means is that f is not an objective tensor. Okay, and this has to do with the fact that if you look at, if you recall what the indices on f are, remember it's a 2-point tensor, it has one index in the current and one in the reference configuration. That is what we're seeing reflected here. Okay? All right, so if we were to write this in terms of coordinate notation, we may see little I, capital I on this. We would have q, little I, capital J, f, j, capital I. What is happening is that the index j, which lived in the current configuration omega t, is being transformed by that further rigid motion on the current configuration to index I. Okay, the index capital I, which lived on the reference configuration, sees no changes on the current configuration. Okay, so that remains unchanged, and therefore we do not have a Q transpose sort of right multiplying this whole thing.